welcome to everybody to our today's online lecture of the Geological Mapping and Modeling Expert Group of EuroGeoSurveys. Welcome to our members and welcome to any guests. Especially a warm welcome to Marc-Philippe Wichmann from BGR in Hanover, the German Federal Geological Survey, so to say. You received the invitation with some information about his person. He is a geologist and paleontologist, but since many years working in the field of geoinformatics, and now leads the Geological General Maps of Germany team and coordinates as well the Inspire implementation at BGR. Thank you for your readiness to give us this lecture. The topic is semi-automatic generalization of 2D geological map data with the acronym AGNES. If you remember, we tried to implement this topic in our ongoing work package 6 of the GSEU project. This was not possible due to budget restrictions, but the good news is that there is an ongoing project, and we are really interested from our community in the developments in that area and have really big expectations. And please give us your lecture.
Okay, yeah, I will do. Yeah, first of all, yeah, thank you very much for your opening words, Hans-Georg, and thanks a lot giving me the opportunity to represent my lecture in this expert group or expert circle. So, as you already said, the theme or the name of my lecture is Semi-Automatic Generalization of 2D Geological Map Data. And as you remember, maybe the invitation, there's a slight difference. I added in brackets the acronym AGNES because in the next 30 minutes, I'm going to talk about our project AGNES, which we are carrying out at the moment at the BGR. Okay, so let's start with the lecture. Let's start with a look at the initial situation which we had at the BGR. And so currently, this is one of the main points, currently the BGR's geological general maps of different scales are not connected to each other in terms of data technology. This is the actual fact. So far, we performed the derivation of small scale maps from large scale maps in a manual way. And this was very time consuming. But to be honest, I wasn't involved in this time consuming work. I'm not very, I'm pretty old actually now, but I'm not so old that I was involved in this manual derivation of the large scale maps from the small scale maps. But I heard from my colleagues that this work was pretty tough and was very time consuming. So that leads us to the objectives of the project. The main goal, of course, of the AGNES project is to establish a connection between the BGR geological maps of different scales in terms of data technology. So the fact is that we need a semi-automated or an automated semantic and geometric generalization procedure, including an automated scale-dependent visualization of the maps. And all this has to minimizing the time required for the generalization. That is, we are looking for the one button, I would call. I can tell you already that we didn't find the one button which can do everything, but what we have found is, I would describe it as kind of a semi-button, which will really helps us to find the right way to get this generalization fixed. Okay, so how does the approach look like? How do we try to reach our goal? As I already mentioned, we have started the AGNES project. The AGNES project, or AGNES, is an acronym or kind of acronym and stands for Automated Generalization. In the framework of the AGNES project, we are using, respectively, we are adapting the generalization tool AutoGen. And this tool was developed at the State Office of Geology, Raw Materials and Mining in Baden-Württemberg, shortly named LGRB. And this generalization tool was mainly developed by Joachim Schuff as part of his master thesis in 2019, and also in cooperation with the German company Quaternary. Maybe some of you already know Quaternary, but this was or the company was also part of the development of this generalization tool. The main object or the main objective in the AGNES project at the moment is the semi-automated or automated derivation of the GK1000. The GK1000 is the geological map of the Federal Republic of Germany at a scale of 1 to 1 million from the GIG 250. And the GIG, the GIG 250 is the geological map of Germany at a scale of 1 to 250,000. Maybe you remember, if you take a look on the abstract of the lecture, there you can read also the expression GIG 200, but at the moment, now we don't have anymore the GIG 200. This is the old map. Now we have the GIG 250, and so the next generalization steps or processes will start with the GIG 250. But in the past, we used the GIG 200 at the base for the derivation of the GK 1000. Okay, so let's go to the next slide. Let's take a look at the AutoGen workflow, and let's take a look how does it work, or how does the AutoGen workflow work in general. Yeah, in total or in general, AutoGen, of course, is a procedure for the generalization of spatial data, for the generalization of polygons, respectively of geologic units, which we have in a geological map, and of course also of line elements, respectively the tectonic line elements. To be honest, at this point, I have to tell you that that I still brainstorm on the generalization of the tectonic line elements. And so for this reason, unfortunately, I cannot go into this part in more detail in my presentation, but hopefully I can report on the generalization efforts on the tectonic line elements in the future on another occasion. But now, or at the moment, we don't have any results in this case. Okay, another thing which is important is that the AutoGen method or the procedure is based on a hybrid solution or on a hybrid approach. That means the AutoGen workflow consists of a vector-based and a raster-based processing. We are talking about this later in my lecture. The individual work or generalization steps are combined in the workflow created with the software FME. I think most of you are familiar with the FME, but I just want to point out what it is. So FME stands for Feature Manipulation Engine, and FME is the spatial ETL software created by the Canadian company Safe Software. And ETL means extraction, transformation, and loading in terms of data. And below you can see the whole FME workflow, which we use to generate our GK1000 map. But on the next slides, we're also going into the different steps, and we take a closer look to the different main steps of the FME workflow. Another interesting thing, or another important thing, is that different functions of the ArcGIS-based geoscaler toolbox, which was developed by the Geological Survey of Canada, bless you, are used for the polygon simplification. And the centerpiece of this geoscaler toolbox, or the heart of this toolbox, is a cellular automata or automaton. And what the CA is, I will explain it to you later during my lecture. So we take a closer look at this on another slide. Okay, so what main steps do we have in the AutoGen FME-based workflow? On the next couple of slides, I will explain to you the main 6, 7, 8 main steps of the AutoGen workflow. Of course, the first main step of the workflow is the data input, as you can see here. You can choose, in case of the data input, between a base layer data or between base layer data and overlay layer data. In this case, we only have base layer data. Even sometimes you have some kinds of maps where you have a base layer and a thin overlayer. So you can input these data, or you can input both type of data. But in this case, we only have a base layer data. So that's all what we have in the case of the GIG250. In this case, the base layer, the GIG250, at this moment, at the beginning of the generalization process, has 166,632 polygons, and this amount of polygons is distributed on 247 different geological units. So at this point, we have the data input, as I said, and you can also see on the slide that we also can input tectonic data. But as I already told you, we don't do this at the moment, or we did, but the results, I mean, there's some kind of K, but they are not complete. So at this point, we don't put the tectonic data into the workflow. But of course, at this point of the workflow, we have to integrate a semantic mapping table, or you can say a kind of a hierarchy table. And this table is an Excel format. And on the next slide, I will show you the semantic mapping table. I think everyone has seen already one of these kind of tables. So every geologic unit, or every single geologic unit, has an ID, an abbreviation, a legend position, or absolute legend position. This is very important. We are talking about this later, why the legend position plays also an important role in the generalization process. And the geological unit has, of course, a name or a notation, like here, like Triassic or Muschelkalk. And on the right side of the mapping table, we have two columns, two extra columns. We have the initial scale column, like here. So we start our process at a scale of 1 to 250,000, because we start with a GIG250. And then we have also a target scale column. This is the GK 1000 scale, so 1 to 1 million. In our case, we have only one target scale or one target scale column, but it's also possible in the AutoGen tool to define up to 3 target scales. But here we directly map from the scale 1 to 250,000 to 1 to 1 million. So in this way, or with the help of the semantic mapping table or hierarchy table, AutoGen knows which geological unit from the initial scale must be mapped to which geological unit of the target scale. For example, if we take a closer look, I mean, I think it's quite obvious. So if we take the Warburg Formation, this has the number, or the value 401 at the initial scale, and the Warburg Formation is mapped on the number 701 in the target scale. And 701 stands for Muschelkalk. So it's quite simple. Warburg Formation is going to be mapped on the Muschelkalk. And if we take the Muschelkalk itself, at the initial scale, it's 701, and it's quite obvious. In this case, Muschelkalk will keep its value, so it's still Muschelkalk. So we have the same number in the target scale column. So that's the way the semantic mapping table works. Okay, so let's go to the second main step of the generalization or of the workflow process. Here you can see the second main step, that is the data preparation. So it's quite simple. And the framework of the data preparation, as I already mentioned, semantic mapping table is joined via the geological unit to the base layer data. And in addition, in the framework of the data preparation, the parameter file is attached to the base layer data. And on the next 4 or 5, actually it's only one slide, I'm going to show you, I'm going to explain you the different parameters which are in the parameter file. So let's take a closer look. Here you can see the different parameters which we have in these files. And you can also read user-defined parameters for the different generalization levels. So normally, if we have different generalization levels, we also pick different values for each generalization level. But in our case, we only have the initial scale level or generalization level and the target generalization level. So we don't have to differentiate in this case. Okay, first of all, we have to select the type of the layer. So you have to select, or you can choose between the base layer and the overlay layer. In our case, we only have one layer, the base layer. So we take P as a base layer. Then you have to define the minimum size of the polygons for each different generalization level. In our case, we only have one, the GK 1000 generalization level. And in this case, we say, okay, the minimum size of the polygon is 1 million square meters. The next parameter, which we have to define, is the smoothing value, or the smoothing value for the polygon outline. This is also depending on the target scale. And that means, the higher the smoothing value is, the smoother will be the outline of the polygons. Yeah? And then we have also 2 more parameters. which we have to define, or which values we have to define. And the first is the number of the neighboring cells in the cellular automat and the grid cell size in the cellular automat. Both are depending on also on the target scale and what the cellular automat does in the framework of the workflow, respectively what the cellular automat does in case of polygon simplification. As I already told you, I will explain it later to you during my lecture. Okay, let's go to the next main step in the workflow. This will be the third main step, and at the main step 3, or at the third main step, we're going to carry out kind of geometry validation. So the input polygons are be checked, for example, for multipartness, for overlapping or self-intersecting. And in this case, or in case of invalid geometries, the workflow will be terminated. So a canceling by incorrect geometries at a later time during the workflow is prevented in this way. Okay, that was the geometry validation. Let's go to the next main step of the workflow. This will be the main step 4, and here we have the first semantic aggregation of the geologic units, or the first semantic aggregation takes place. That means that neighboring polygons with the same target geologic unit, or with the same target lithostratigraphic unit in this case, are dissolved into one polygon. As you can see here, we have an example. I use my cursor. On the left side, we have the GIG 250, or 2 polygons of the 250. We have one polygon with the lithostratigraphic value mittlerer Muschelkalk, and another one has the value GMO, that is oberer Muschelkalk. And because both have the same value in the target scale, that means both have the value in the target scale, and they have the value Muschelkalk, we can dissolve them already. So at this step of the workflow, as I said, the first semantic aggregation takes place in this way, or in this manner. Let's go to the next step. This is a little bit more complicated, or at this step, at main step 5, further analyses are carried out. That means more polygons are dissolved. Sorry. As you can see here, sorry, on the left-hand side, here we have a polygon with the lithostratigraphic value Buntsandstein here, and this polygon, or this Buntsandstein polygon, is below the defined minimum size. In our case, as I already said, we have a minimum size of 1 million square meters. So it's below this size. So it's dissolved into its surrounding neighboring polygon. There's only one neighboring polygon, so it's quite easy. Buntsandstein, the polygon Buntsandstein, is dissolved into the Muschelkalk polygon, its surrounding polygon. Another case, also displayed here, is that we have a we have a elongated, a thin polygon, which belongs also to the Buntsandstein, but it's very long, so it's above the minimum size. But because it's so thin, it's almost it's pretty hard to, or it's not possible to display this polygon, or this elongated polygon, in the target scale. So for this reason, this polygon is also dissolved into the Muschelkalk polygon. So at the end of this process, as you can see here on the right-hand side, we only have one polygon, the Muschelkalk polygon. These are simple situations because in both cases we only have one neighboring polygon. So it's quite easy to find the right solution or a meaningful dissolution for these small or elongated or too elongated or too thin polygons. On the next slide, we have a more difficult situation, or at main step 6, we have a more difficult dissolving, or a more difficult dissolving is taking place. In this case, as you can see, we have a Muschelkalk polygon on the left side here in the middle, which has two neighboring polygons, the Kuiper polygon and Buntsandstein polygon. The Muschelkalk polygon is below the minimum size for the polygon size, so it's 0.75 million square meters, so it has to be dissolved. And the Kuiper polygon has a size of 1.5 million, and the Buntsandstein has a size of 3 million square meters, so it's quite obvious because Buntsandstein is a bigger neighboring polygon. So we dissolve the Muschelkalk polygon into the Buntsandstein polygon, which you can see here. But as you can see here, also, I pointed out the legend position. As we remember, when I was talking about the mapping table or the hierarchy table, we had also a column which called legend position. And in this case, I've written here the legend position. So the legend position for Kuiper is 30, for Muschelkalk it's 31, and for Buntsandstein it's 32. And as you can see here very clearly, the difference between the different legend position is always like 1. Between Muschelkalk and Kuiper is 1, and between Muschelkalk and Buntsandstein it's also 1. So in this case, only the size of the polygon, of the neighboring polygon, is important for the direction of the dissolving. Okay, but on the next slide, I will show you a different situation where the legend position, or the absolute legend position, plays a more important role. So let's go to the next slide, or to the next dissolving situation. On this slide, as I said, we have a different situation. We have here in the middle, like before, we have the Muschelkalk polygon, which is below the minimum size of 1 million square meters. But the largest neighboring polygon in this case is the Schwarze Jura-Gruppe, which belongs to the Jurassic. And here we have the Buntsandstein, like before. And in this case, we have differences of the legend position. Because if we take a look here, like before, Muschelkalk has a position 31, the Schwarze Jura-Gruppe has a legend position 28, and Buntsandstein has a legend position 32. So between Muschelkalk and Schwarze Jura-Gruppe, we have a difference of 3. And between Muschelkalk and Buntsandstein, we have a difference of 1. So in this case, because of the difference, we say, okay, it's obvious, we have to dissolve Muschelkalk into the Buntsandstein, or the Muschelkalk polygon into the Buntsandstein polygon. Yeah? Despite the size of the polygon. Because as you can see here, the Schwarze-Jura-Gruppe has a double size of the Buntsandstein-Gruppe, but in this case, the size isn't important. The important fact is the legend position. But not only the legend position or the legend position difference is crucial in this case. In this case, it's also important the parent class, or in this case, the parent class comes into play, because the parent class of the Schwarze-Jura-Gruppe is obviously is the Jurassic, and and the parent class of the Muschelkalk and the Buntsandstein is a Triassic. And so in these cases, as I said, the legend position and the parent class are used together to ensure that we have a semantically meaningful dissolution. So it's not possible that because of the size that we are dissolving the Muschelkalk polygon into the Schwarze-Jura-Gruppe, because that wouldn't make any sense, because it would lead to stratigraphically incorrect. Okay, so let's go to the next main steps. But before we go to the next main step, I have to talk about what I already told you about a switch between vector-based and raster-based processing. At this point in the workflow, we're going to switch between the vector-based and the raster-based processing. So we go from polygon format to a raster format. And I've written down a quote here to explain it from Peter and Weibel from 1999. And they say, in case of a vector-based processing, the dependencies and complexities to be taken into account are significantly higher than with the raster-based processing, in which adjacent areas have topological consistencies with each other per se. So for this reason, we are switching at this point from a vector-based processing to a raster-based processing to simplify the geometries, to simplify the polygons. And at this point of the workflow, we use the GeoScaler toolbox and the cellular automat. And I can say that the cellular automat is kind of the centerpiece, kind of the heart of the polygon simplification. So on the next slide, you can see a cellular automat. And a cellular automat is a temporal or spatial discrete system. And this discrete system consists of regular grid with uniform identical cells. And each cell can adopt each state out of a finite number of states. In our case, this finite number of states are the lithostratigraphic units. And a new state of a cell depends on the rule of calculating the new cell state, its neighborhood, and of course in its state itself. So the neighboring cells influence the cell state. And here on this slide, you can see an example for the initial state of a cell grid. Here, that would be the left grid. And maybe as you remember, I was talking in case of the parameter file, I was talking about the Muir radius. And in the right cell grid, here we can see the blue rectangles. You can see different values of the Morse radius displayed by the blue rectangles. So the inner rectangle, the inner blue rectangle, represents the value 1. So in this case, 8 neighboring cells influence the state of the raster cell, which are marked with a question mark, and the outer blue rectangle has the Morse radius 2. So in this case, 24 cells influence the state of the cell which are marked with a question mark. And of course, also the size of the cells, which are marked out also in the case of the parameter file, plays a role. Okay, so hopefully you got this, how the cellular automat works. If not, I think we can also talk about this later during this discussion. But let's go to the next slide. And here we are coming to the process of nibbling. Because an additional main factor besides the Moore radius and the cell size in the grid is the number of iterations. So how often or how many times the state of a cell is calculated. Here on the left side, you can see the cell grid state for different examples. So you can see the example here right in the middle for 1 iteration, for 2 iterations, and for 3 iterations. And this process called nibbling. So that means that iteration by iteration, the CA, the cellular automat, is nibbling on the outlines of the polygons. Respectively, CA is simplifying the outlines of the polygons. So in our case, we decided to regard that 80 iterations are a good value. We can talk about this later when I'm going to show you our preliminary results. Maybe 80 iterations is not the perfect amount, but yeah, maybe it's discussable. But in our case, we decided to run 80 iterations for the best results. Okay, so if we go to the next step or to the next main step, here once again we have a switch between the raster-based processing and the vector-based processing. So we go back from the raster to the polygon. So after running 80 iterations, we switch again, and we're going to receive a result as a vector file. And this result you can see here on the next slide. So as you remember, in the beginning of our generalization process, we had at the 250 scale, so at the initial scale, we had 166,632 polygons distributed on 247 geological units. And now at the end of the generalization process, we have only 19,157 polygons belonging to 253 lethal stratigraphic units. Maybe you're wondering why I'm saying in case of the 250 geological units, and in the case, oh yeah, I see. Oh, sorry, there's a mistake here where the cursor is now. Of course, you can read 250. That's not correct. I thought I have to correct it, but of course, in this case, we are talking about the GK 1000. So, as I said, maybe you're wondering why I'm talking in the case of the 250 on geological units and in the case of the GK 1000 on lethal stratigraphic units. The reason is that actually at the moment, in case of the 250, we have only, we display the 250 in the way of 3 thematic maps. So we have the chronostratigraphic theme, the genesis theme, and the petrography theme. So we don't have in real a good 250 with lethal stratigraphic units. So that's the reason why I'm talking about only geological units in case of 250 at the initial scale, but in case of the GK 1000, we have real lethal stratigraphic units. Okay, so you can see the big difference between the starting situation and the situation after our generalization workflow. So that leads us to the preliminary results, which we have achieved so far. So here you can see 2 test series with different parameter values. The upper test series was performed using the original parameter values, which are recommended by our colleagues at the LGRB in Baden-Württemberg. I mean, our colleagues at the LGRB in Baden-Württemberg, they did also a lot of test series, and then they decided, okay, they found the perfect combination of parameter values, which leads to the best result. But in our case, we played around a little bit and we adjusted some parameters. So in the lower test series, which you can see here, was performed by using modified parameter values. For example, a lower raster cell size or a higher smoothing value. But in both test series, we carried out 1, 20, 40, or 80 iterations. Okay, so that was not the only thing what we did in the framework of the AGNES project. We also did test series with different parameter values in different areas to determine the best combination, as I already said, of parameter values. And so on the left side of the slide here, almost in green, you can see the Kiel Canal area. The Kiel Canal area actually is shows the area of the channel which connects the Baltic Sea and the Northern Sea, but the official name of this channel is the Kiel Canal. So you can see it here on the left-hand side. And on the right-hand side, you can see the already familiar to you area located between Bavaria and Baden-Württemberg. And as I can say, in total, actually, we are quite happy so far with the results that we achieved, but there are some potential, sticking points. And these sticking points you can see on this slide. So one sticking point are the polygons below the minimum size of 1 million square meters. which we have, and they are hold here in the color pink. I mean, as I said a couple of times, we defined a minimum size for the polygons in the target scale for the GK 1000, but because of the nibbling effect, or because of the nibbling process, in the end, we have, as you can see here, in both test areas, we have pink polygons which are under the minimum size of 1 million square meters. I mean, this is, as I said, this is a kind of a nibbling effect. Maybe this is also the effect of the amount of iterations which we are carrying out. So maybe we have to reduce iteration or the number of iterations. As I said in the beginning, or actually we think 80 iterations are a good number. Maybe we have to reduce the iterations, but if we reduce the iterations, we're going to have other effects, which possibly are worst. So as you can see, always it's also some kind of compromise which we have to find. And another potential sticking points are polygons which are too thin, especially the river or the Quaternary river and lake deposits, which you can see here, marked by the dark blue arrows, like here, or also like here and here. And this is the effect, or the reason is that, as I told you, we are nibbling the outlines of the polygons in the workflow, and we don't have the possibility to enlarge polygons or to blow them up, to make them bigger, like in former times. Or if you do it manual, you can say, okay, I have a thin Quaternary river or lake deposits. I just make it by hand bigger, the polygon. In this case, we can't do it, or we can do it in the framework of the workflow. I mean, a solution would be maybe that we add some extra function who would can do this, but at the moment, we have to live with that. Okay, but nevertheless, I would like to say that we have achieved, I think, some good results so far. And besides, let's go to the next slide. Besides the preliminary version of the GK 1000, we also produced, we have also some other results at the moment. So we produced 3 preliminary versions for the GK 1000. So in fact, we have the theme Genesis, we have the theme petrography, and we have also the thematic map chronostratigraphy. And that leads me to the final, I think it's already the final slide of my lecture. So this way, maybe we have more time for the discussion, to the upcoming work and to a short outlook. So the work which is still to be done, of course, is this generation of the final version of the lethal stratigraphy, and also the work to do the final versions of the Genesis, the petrography, and the chronostratigraphy. And like always, we also have to do for every theme, and also for the lethal stratigraphy, we have to do Inspire compliant version for all of these maps. And of course, as I told you almost in the beginning of my lecture, of course, we have to integrate the tectonic line in elements into our maps, into our final versions, of course. And possibly or hopefully, in the future, we can also use the AutoGen workflow to provide the German part of the EGSGMMEG 2500. EGSGMMEG 2500 is an international quaternary map of Europe and the adjacent areas. And hopefully, indeed, we can use also the AutoGen workflow to provide the German part of this map also in the future. Okay, I think that's all from me at the moment.
Thank you, Mark.
Thank you very much for your attention.